Good morning and welcome everyone to the Patriot Emerging Technologies educational webinar. My name is Steve Cronin and I am the Vice President and co-founder of Patriot Emerging Tech, and I'm your host for the next 90 minutes. We're very excited to have you all joining us today. Very appreciative that you're taking the time, considering the fluid nature of the pandemic and the scope of your preparation to receive students in about six to 8 weeks. Our discussion this morning is specifically tailored to address a critical challenge faced by university and college executives and staff, now exacerbated by COVID, and we are very fortunate to have two proven and experienced industry leaders with us to help walk through our topic, how to reduce Opex in higher education. First, I'd like to introduce our speakers today. I, again, am Steve Cronin with Patriot Emerging Tech. I'm here with my partner, Bill Bockoven, President and co-founder of Patriot. And I'm very excited to introduce our featured guest speakers, starting with Mike Mushaty, an enterprise account executive from Bloom Energy. Mike has an electrical and computer engineering degree from URI, then spent a number of years in an engineering and consultative sales role at APC, Schneider, and then Eaton. He ran a global critical facilities team for Tower Research Capital, and for the last 9 years has been with Bloom in a strategic account executive role, working with higher education and Fortune 500 customers. Next, we have Deandra Aversa, an account executive from STEM. She has spent the last 7 years in the clean distributed energy space, working with Fortune 500 and higher ed customers on energy storage, solar, and fuel cell solutions. Finally, we have Dana Christensen, a senior product manager from STEM. Dana is responsible for product roadmap, product strategy, and end-to-end delivery of forecasting for STEM's Athena AI platform. Dana has a BS in chemical engineering from Northwestern. Our agenda this morning will be 10 minutes with Bill to provide a snapshot of Patriot Emerging Technologies, followed by Mike at Bloom Energy for 30 minutes, and then 30 minutes with Deandra and Dana from STEM. They will both be providing a brief introduction to their company and touching on their solutions, but with a focus on how those respective solutions can make a big impact on reduction of operating expenses. We will then proceed to a Q&A to wrap up no later than 12 p.m. But before I pass the ball to Bill, I want to touch on a few housekeeping items. First, we do, as I just said, we're going to have a Q&A for the last 15 minutes of the webinar. In lieu of opening up microphones, which can get, frankly, pretty chaotic, please type whatever questions you have. I will consolidate and then address the questions to the appropriate person or persons during the Q&A period. If we run out of time to get to all questions, they'll all be captured and answered via a group email sent to all attendees after the webinar. Finally, please feel free to reach out to Bill or I after the webinar with questions, comments, or if something that you're about to see makes sense to evaluate on your campus. So at this point, I'd like to introduce Bill Bockoven, President and co-founder of Patriot Emerging Technologies.
Yeah, thanks very much, Steve. Thanks to everybody attending our call today, and welcome to our webinar, Lowering Opex in Higher Education. We all know we're in unprecedented times with this current pandemic. We understand that colleges and universities are under massive pressure to build a reopening plan, including testing, social distancing, online learning. I mean, we're hitting our high in a lot of states, and there's still an awful lot to do. We also know that energy teams that can reduce their Opex by several $100,000 to $2 or $3 million per year without putting any capital down are now being recognized by their leadership teams as very strategic to their organizations moving forward. And we really appreciate everybody spending time with us today, really discussing how colleges and universities are leveraging two technologies, enterprise storage and fuel cells, to reduce Opex and deliver sustainability benefits as well as resiliency to their campuses. So just as some background, at Patriot Emerging Technologies, we help customers generate power on site that's cheaper, cleaner, and more reliable than their grid. For over 2 decades, Steve and I have helped deliver roughly 160 megawatts of projects across 300 sites and 75 individual microgrids to lots of different customers, from federal customers like the Department of Defense and the NSA, the National Institutes of Health, to commercial companies like Home Depot, Cox Communications, and Partners Healthcare, to universities like Fordham, Connecticut College, and Long Island University. And At Schneider, our focus was mission critical power solutions for data centers and land rooms. And then at Bloom, a solid oxide fuel cell solution, which we'll be talking about today. Our vision, we like this slide because obviously our vision is really to help customers build an enterprise energy strategy, leveraging innovative solutions, but solutions that are proven in the distributed energy area. So not just the status quo, trying to go to where the puck is headed. From a solutions standpoint, we offer best of breed technologies, the leaders in these industries, from fuel cells to on-site solar, battery storage solutions, to electric vehicle charging stations, as well as fleet charging. From a consulting services standpoint, I mean, we've got a track record that can help companies and schools really understand, you know, for your goals and your project, and based on what your load looks like, your load curve, and where your future is headed, we can help you understand what's the right fit for you. It's not a one size fits all. It's what is the right solution depending on your requirements and your load and what you're trying to do from a sustainability standpoint, a reliability standpoint, and a cost-cutting standpoint. We can help customers understand their loads, size a solution, understand their financial models, both from a technical standpoint and a financial standpoint, understand utility market forecasting and where the risks of these projects lie in terms of the financial model and in terms of the technical sales. So we think we're uniquely situated with our background to help you through and make the right decision, and then present the right solution to your leadership team and help you all the way through the project itself. So that's a quick snapshot of Patriot. Thanks again to all of our attendees and presenters today for making this a great event. Really appreciate it.
Thank you, Bill. So now at this point, I'm going to pass the ball to Mike Mushaty at Bloom. And during this screen transition, I just want to remind you to please type any questions that you may have so I can aggregate them. Mike, I can see your screen.
Thank you, Steve.
All set.
Introduction. And first and foremost, I'd like to thank everybody for attending today. It's not lost on me that you have a lot of competing priorities right now, not just with your regular day-to-day jobs, but obviously with the pandemic throwing a bunch of things on top of those responsibilities. And I'd also like to thank our technology partners here today. First and foremost, Patriot Emerging Technologies for putting this together and hosting the webinar, and also for STEM for partnering with us today in sharing this presentation space with us. So for a quick agenda here, I'm going to give a quick overview on Bloom, who we are, what we do, and who we do. I'm going to talk a little bit about the technology, hopefully share some insights as to what's going on in the higher ed space with respect to what we're seeing in our business. And then lastly, I'm going to kick it back over to Steve Cronin, and he will be playing a video done by our Director of Enterprise Systems Engineering, where he gives a virtual tour of a Bloom Energy server actually operating. So first and foremost, who or what is Bloom Energy? Bloom Energy is a solid oxide fuel cell manufacturer headquartered in San Jose, California. For those of you who don't know what a solid oxide fuel cell is, in short, it's a magic box that converts natural gas to electricity without burning the gas. And we're going to talk a little bit more about that magic box further in the presentation. We incorporated in 2001, so we've been around for almost 20 years, and we are publicly traded on the New York Stock Exchange as of summer of 2018. The majority of our customers are in the Fortune 1000 and or in the higher ed or nonprofit space. We boast 25 of the Fortune 100, and we've installed systems at over 600 sites nationally here in the United States. We're also an American manufacturer. We manufacture all of our systems out of our manufacturing plant in San Jose, California, so supporting our West Coast operations. And we also have a world-class manufacturing facility in Newark, Delaware, supporting our East Coast operations. So that's a little overview of who Bloom Energy is. You know, with respect to the higher education space, at the risk of stating the obvious, it's been a very interesting 6 months. I've heard, you know, if you'll go back in time with me starting in January. A lot of the executives at my higher education customers were still conducting business as usual, focused on doing projects, so forth and so on. And the pandemic and the virus were largely background noise. And we started to see a shift in February. We started to hear things like, I have a case on campus, or my university system is starting to prepare for the possibility of a pandemic. And then March, things got very real very quickly. In a couple of instances, we heard the sentence, I have an outbreak on campus. I can't talk to you right now. I need to deal with that. And then shifting to April and May, I heard things from my customers in the higher ed space that I honestly never thought I would hear in my entire career. Things like, the National Guard has commandeered my campus. My campus is now a pop-up tent hospital. FEMA has taken over my campus. My campus is now a COVID-19 testing site. And there's various iterations of those, some more extreme, some less extreme, that we've heard from executive stakeholders at our higher education customers. And that has then shifted again to June as we learn more and more about the virus and the pandemic. It has shifted to more, instead of panicked statements, more questions. Are students coming back? What is my energy load profile going to look like? Are we going to be running virtual courses or doing remote learning? And now most recently, getting to the point of the webinar, which is reducing operating costs, we've heard things like revenues are dropping. We've heard things like, I'm now running the biggest deficit in my school's history. So the long story short is a lot of the stakeholders in the higher education space are now focused on mitigating the increased operating costs associated with the pandemic, looking for opportunities to reduce operating costs without having to make a large upfront capital investment. And that's where Bloom Energy comes into play. Via our power purchase agreements, we enable higher education customers to not only lower their energy costs by 10 to 20% without any upfront capital investment, but also keep energy costs predictable by eliminating or drastically reducing energy cost volatility. This gives the finance folks at your institutions the financial predictability that they so desire when it comes to operating costs. And obviously the reduction in operating costs is very attractive given everything that you're dealing with right now. In addition to strictly lowering your operating costs on the energy side, we also have the capability to reduce not only operating costs, but possibly upfront capital costs associated with legacy critical infrastructure, backup generators, UPSs, batteries, and the like. Whether you're using that infrastructure to back up dormitories or critical campus facilities, or you're looking to divert those resources to new data centers or computer rooms to support remote learning, and or divert those resources or purchase new resources to power the pop-up tent hospitals or COVID-19 testing sites, we have the ability to deliver those solutions again with no upfront capital expense, helping you recoup those capital expenses and the obvious ongoing operating costs associated with diesel generators and legacy critical infrastructure. Lastly, one thing that we've heard a lot from key stakeholders in the higher ed space is parents and students alike are more focused on sustainability. They want to see that universities and colleges are doing the right things on campus to mitigate their environmental impact. And we've also seen some universities and colleges go as far as to develop new programs around environmental studies for their students to participate in. So the long story short is Bloom Energy checks a lot of boxes for higher ed institutions today. Without any upfront capital investment, we have the ability to lower your energy costs, reduce energy cost volatility, reduce upfront capital and operating costs associated with legacy critical infrastructure, while also making your institution more attractive to students and parents that may be deciding to attend your institution in the fall as opposed to a different institution. And as you can see, we've been successful in this space. From coast to coast, whether it's Caltech, the SUNY Downstate Medical Center in Brooklyn, Long Island University Post, Fordham University. Literally from coast to coast, we have delivered these benefits and these solutions to higher ed customers. And we look forward to engaging with yourselves as well when the time is right to see if we can deliver these benefits for you as well. One other thing to mention is in many states where we operate, there are a lot of incentives available to higher education customers that move forward with Bloom Energy projects. This is particularly attractive in the midst of a pandemic because while the Power Purchase Agreement program is a no upfront expense program, some of these incentives pay upfront in either cash or they'll pay ongoing in terms of cash rebates. So in addition to being able to reduce costs without any upfront expense, you may also be handed a big bag of cash by either a utility or a state government for doing the right thing and moving forward with a Bloom Energy project. You'll notice conspicuously missing from the slide is the state of California. We used to be part of the California Self-Generation Incentive Program. What's interesting about California is the market dynamics are such that we have since more or less graduated from that program. So while you will not receive any incentives for a Bloom Energy project in California, the market conditions are such that you are already incentivized to be doing projects with us. And these market conditions specifically are rising electric utility costs combined with the electric utilities sometimes turning off the electric grid for days at a time for public safety power shutdowns to help prevent wildfires in the state of California. So long story short is across the nation, there are many incentive programs available for Bloom Energy projects. And there's also a lot of states where the projects make sense without incentives as well. So I'm now going to transition to talk a little bit about the technology itself. The core component of the technology is the fuel cell. The fuel cell itself is the tile I'm circling with my laser pointer here. That tile you could hold in your hand. It's actually quite small. It's about 10 centimeters by 10 centimeters. And that tile can produce about 25 watts worth of power. How does that tile produce 25 watts worth of power? Well, the easy way to think about a fuel cell is to think of it as a battery that will always produce power as long as natural gas and ambient air are available to the fuel cell. And the way this works is we will take natural gas right off the street, and the core component of that natural gas is methane. That's what's important to the Bloom system. I mentioned before that this is a magic box that turns natural gas into electricity without burning the gas. Well, then how do we do it? We do it via an electrochemical reaction. And the electrochemical reaction takes place right on the electrolyte of the fuel cell itself. The electrolyte is a ceramic tile. The green ink and the black ink, we silk screen onto the electrolyte. Again, sticking with the battery analogy, the green ink acts as the anode, the black ink acts as the cathode. So what I'm going to do here is I will take the methane, the core component of the natural gas, I'm going to blast it with steam to create a reformed fuel stream consisting of hydrogen and carbon. On the cathode side, I'm going to introduce oxygen from ambient air. And when I have oxygen floating on the cathode side and the reformed fuel stream floating on the anode side, all of these molecules get very excited. And the electrolyte is the dance floor where all the magic happens. So effectively, you're going to see the oxygen marry up with the carbon and marry up with the hydrogen. And this is going to create a number of byproducts via this electrochemical reaction. One of the byproducts are electrons that get freed. These electrons flow to your building. They are the electricity that the system produces. The other byproducts are a small amount of carbon dioxide, which does get emitted to the atmosphere. The other two byproducts, heat and water, stay internal to the system to generate the steam that I need to break apart the carbon from the hydrogen and the methane at the beginning of the process. So as you can see, this is a complete balance of plant process. There's no combustion. And while we do have a small CO2 footprint, we have none of the harmful air pollutants and air particulates that is traditionally associated with combusting fossil fuels on the electric grid. Because we're not using combustion to generate electricity, and we are using this electrochemical reaction, we are roughly twice as efficient as the electric grid at turning natural gas into electricity. Now, that little 25-watt fuel cell is not very useful in of itself, unless you're looking to power like an LED light bulb, right? So how do we go from a tiny little 10-centimeter plate to a multi-megawatt power plant? Well, the way we do it is we take that fuel cell plate and we will make a big fuel cell sandwich that we call a stack. And this sandwich is effectively just metal interconnect plates sandwiched with fuel cell tiles over and over and over again until you have a nice brick that you see in that second picture that you could hold in your hand. That stack that you could hold in your hand is a little heavy, weighs about 10 pounds, and that can produce about 1 kilowatt worth of power. We then aggregate these stacks into what we call power modules. These power modules are 50 kilowatt independent power modules. We aggregate multiple power modules to generate a system. Our system sizes are 200 kilowatts, 250 kilowatts, and 300 kilowatts. And we will take those system sizes and parallel them together to achieve multi-megawatt scale. So for example, if you need a megawatt worth of Bloom Energy power, we would parallel together 4 250 kilowatt systems. If you need 3 megawatts of Bloom Energy power, we would parallel 10 300 kilowatt Bloom Energy servers. So that's how we go about taking a 25-watt tile and turning it into a multi-megawatt power plant. Just to give you an idea in terms of scale, we do projects as small as 200 kilowatts, which you would typically find behind a large retail establishment like a Home Depot or a Walmart or an IKEA, all the way up to multi-megawatt utility scale applications. Our largest single site installation here in the United States is 27 megawatts in the state of Delaware with Delmarva Power. And we do projects everywhere in between that 200 kilowatt footprint and that big 20, 30, 40 megawatt utility scale power plant type of project. So a little bit more about the technology here. What does it look like? How does it work, right? What you see here is a picture of a 250 kilowatt energy server. The 250 kilowatt energy server consists of 8 4-foot by 4-foot modules. Think of these modules as Legos. They can be snapped apart and manipulated as you see fit. So the footprint you see here is 32 feet by 4 feet. I could manipulate those Legos so that it's 16 feet long by 8 feet deep, just as an example, and a variety of combinations that we're not going to discuss here because of time. These 8 modules serve different purposes. The first module is what we will call our input-output module. That's where the electricity that's generated by the fuel cells is inverted to AC power from DC power and delivered to your facility. The second module is my gas module. That's where I'm going to take in the natural gas feed. I'm going to knock down the pressure. I clean up the natural gas a little bit, remove some of the constituents that aren't methane that the natural gas company injects into the pipeline before the natural gas actually goes to the power modules for electricity production. I also have 6 independent 50 kilowatt power modules, all linked together on a common DC bus. And you're probably thinking, this guy does not know what he's talking about. 6 times 50 is not 250. Well, you'd be right on both accounts. 6 times 50 is not 250 kilowatts, it's 300. The reason we call this a 250 kilowatt energy server is because the extra power module allows us to act and feel like the traditional legacy critical infrastructure systems that you're probably accustomed to currently serving your critical operations on campus. This level of redundancy gives us a level of fault tolerance in case we have an issue with an individual power module. It does not disrupt the fully rated amount of power being delivered to your facility. It also allows us to do concurrent maintenance. We are going to turn the system on. It is going to produce power 24/7, 365, and we are not going to turn it off for the full 20-year life of the system. we can do all of the maintenance associated with the system without ever disrupting the fully rated amount of power to your facility. I can literally replace every single one of those fuel cell tiles in the system without ever disrupting the fully rated amount of power to the facility. As discussed earlier, we are converting natural gas to electricity without combustion. This makes us the most efficient way on the planet to convert a fossil fuel into electricity. Our starting efficiency, LHV, is 65%. Again, compared to the efficiency of the electric grid here in the United States, we are roughly twice as efficient as the electric grid at converting natural gas into electricity. This is why we are less expensive than the kilowatt hours you would otherwise purchase from the electric grid. This is also why we are so much cleaner than the kilowatt hours that you would otherwise purchase from the electric grid. And in summary, Bloom Energy is uniquely suited to address both the causes and consequences of climate change. The causes being greenhouse gas emissions being emitted into the atmosphere. We have a significant reduction in greenhouse gas emissions running on natural gas. Depending on where you are in the country, we will represent a 20% to 60% reduction in carbon dioxide compared to the electric grid. We are also a 100% reduction in all of the harmful particulate and air pollutant associated with combustion technologies. We also have customers that elect to run our systems on directed biogas, in which case we are a 100% renewable project, and you can claim a 100% reduction in carbon dioxide in addition to all the other benefits that I described. A dirty little secret about the electric grid is it uses about 1 gallon of clean water per kilowatt hour generated on average nationally. Bloom Energy servers do not consume any water at all under normal operation while we're generating electricity for your facility. Those are the sustainability benefits that we can provide today that help combat the causes of climate change. Looking towards the future, we are working in carbon capture technology to help projects that are running on natural gas achieve a zero carbon footprint. And the systems are also capable of running on renewable hydrogen if we do someday turn to a hydrogen economy and hydrogen suddenly starts displacing natural gas in the natural gas pipes that exist today. From a consequences of climate change standpoint, we have the ability to run independent of the electric grid during an electric grid outage indefinitely for weeks or months if need be. So again, we are uniquely suited to address the causes and the consequences of climate change for your facilities on campus. And Steve, with that, I would like to hand it back over to you to play the virtual tour of the Bloom Energy server.
Thank you, Mike. Very well done and accessible content. Appreciate that. Okay, I'm going to share. Okay, can you see my screen?
Not yet.
Okay, bear with me. Having a slight technical difficulty. Okay, wait a minute. Oh, Mike, why don't we hit the pause on that for now? Let me work on this, and in the we can circle back on the video, if that makes sense.
That sounds great.
Okay, and in the meantime, I'm going to pass the ball over to Deandra and Dana at STEM.
Sure, thanks, Steve. Let me know when you can see my screen.
It's up. Thank you, Deandra.
Wonderful. Well, thank you everyone for joining today. I hope to have the opportunity to speak with many of you following our presentation. Thank you to our partners at Bloom and for Patriot for putting on the webinar today. Again, this is Deandra Aversa with STEM. My colleague Dana Christensen and I will be talking through the multiple layers of STEM's value today, specifically in the context of today's world of economic uncertainty. Before we get into those technical details, I'll take a couple minutes just to set the stage of who STEM is and what we do to kick it off and set the context here. So who is STEM? STEM operates an artificial intelligence platform for energy storage optimization. Our technology, our intellectual property made in-house, is a machine learning algorithm. It's our software called Athena. And at STEM, we layer that software, we layer Athena on a hardware system, which is generally a large battery and ancillary equipment. And STEM software tells the battery when to charge and discharge to adapt to real-time changing conditions on site. For example, what are variable weather patterns day to day? What are changes in a facility's load throughout the day and week and year? And that software controls the charge and discharge of the hardware to optimize the timing of energy use on site and ultimately save our customers money while aiding in resiliency and sustainability efforts at the same time. As a company, we've been around for a bit over 10 years now, headquartered in the San Francisco Bay Area. Our operations are primarily concentrated today in California and the Northeast of the US. We have over 1,000 customer sites currently, totaling nearly 800 megawatt hours. And through this extensive customer base and backed by a host of high caliber global investors, STEM today operates the largest energy storage network in the world. So that's a bit about our company, who STEM is. And so STEM works with companies across a variety of different industries and verticals, higher education included. And as COVID-19 has, as discussed, recently spread throughout the world and effectively reshaped our global economy, at STEM, we sought out to understand how this crisis is impacting our client base and how our customers are responding to these challenges across all verticals. So based on this research, conversations with customers and other industry experts, we have heard responses coalesce around a couple of themes here, around the themes of risk management, first and foremost, around digitization and automation, and operational excellence. After keeping students, faculty, employees safe, leaders are clearly looking to ways to become more efficient and cut costs to weather the hopefully temporary storm we're dealing with. We're also hearing that sustainability and resiliency are becoming more top of mind issues for schools, for prospective students, families, and that organizations are accelerating sustainability efforts to differentiate themselves and win that kind of brand loyalty. So based on that research and our understanding of the current context, we've identified a couple of key strategies here that we think will be helpful for business leaders like yourself in what we're calling recession-proofing operations and facilities. First, reducing operating expenses and identifying cost-cutting solutions that produce immediate returns without upfront capital involved. Second, automating operations where possible, leveraging tools like artificial intelligence and remote monitoring to keep operations running smoothly while students and faculty may be working remotely for a temporary period. Enhancing resilience so facilities can more quickly and flexibly adjust to these economic and environmental or market changes going forward. Increasing operational efficiency through continuous process improvement and, importantly, technological innovation. And finally, again, building that brand loyalty by making reliable, data-driven decision and incorporating feedback. So to help set the context of how energy storage can help address many of these issues in these business priorities discussed today, I'd like to spend just a few minutes touching upon a few macro level issues that operational leaders are facing today, specifically with regards to their energy strategy. So we are expecting renewables, solar deployments to continue to grow exponentially in 2020 and beyond, despite COVID. And as a result, this new and increased renewables penetration will continue to change how the grid operates and how utilities as a result have to invest in infrastructure to ensure continued grid stability with these changes. We've put a little visualization of an example on this slide here. In some utilities in which STEM operates, we've seen in recent years a shifting of peak periods from previously midday to later afternoon, early evening to accommodate that influx of solar in the middle of the day, and again, balance that supply and demand equation. So as a result, we are seeing that electricity cost is increasingly dependent on when you use energy, not just how much energy is used, not just the quantity. In some regions where STEM operates, for example, we're seeing north of 50% or so of our customers' electricity charges based solely on peak demand. And as mentioned, these peak time windows are shifting and are pretty certainly guaranteed to continue to shift in the future in response to changing grid conditions. And utilities to keep up and to balance, again, that supply and demand will need to continue to adjust rate structures to ensure this rate recovery amid greater renewables penetration that is foreseeable to continue and if not accelerate in the future. So more and more, in light of all of the options that you have today at your disposal, from fuel cells to battery storage, solar, EV charging, more and more we're finding that business and organizational leaders are wanting these energy systems connected so that they can manage them holistically and more efficiently. So energy storage in this context is seen as the technology that is most adaptable and most flexible to be paired with other solutions as well to enhance their appeal. For example, energy storage can enhance the value proposition and the return on investment of a solar system by charging off of that PV and shifting those kilowatt hours to peak periods later in the day. As one example. And storage can also help mitigate the high demand charges associated with EV charging. So we're seeing organizational leaders in this sense come to adopt energy storage as a way to help address many of these issues that both organizations, businesses, utilities are facing today, particularly amid the effects of COVID. First and foremost on the economic savings front, which is really the backbone to many of these projects, storage has helped our customers generate immediate cash flows by reducing utility expenses while ensuring they maximize values of other assets that we mentioned, like solar on site, EV charging infrastructure, et cetera. In addition to increasing these projects' ROI, storage future-proofs other technology investments that may be subject to the changing rates that we discussed. That's really an unpredictable element of future utility rates. On the resiliency front, energy storage can be deployed to provide a facility a greater level of resiliency against interruptions in power supply, be it either from shorter duration outages to irregularities in voltage on site that can all be disruptive to operations. And finally, both utilities and the environment appreciate energy storage and the benefits of energy storage as well, in that the electric grid simply cannot handle the addition of all of the renewable power coming online without energy storage being part of the equation to balance that supply and demand. So at STEM, we engage in these sorts of customer conversations as much as possible and are really committed to helping our customers achieve each of their unique business objectives. Each customer we work with is unique. Each system configuration, each site is unique as well. But customers are consistently telling us that energy storage helps them in a variety of ways, ranging from lowering operational costs, like we discussed, enhancing resiliency on site, demonstrating innovation, for example, and also aiding in sustainability efforts, as we discussed. So I wanted to just touch for a minute or two on one example of a STEM customer in the higher education space who captured many of the values that we've discussed today. At a high level, STEM has 26 current customers in the higher education space, totaling 37 megawatt hours. One example here at Santa Rosa Junior College, a couple of years back, the college developed a facilities master plan that included a solar plus storage strategy. At the time, the college and the facilities department recognized that intelligent energy storage is a natural complement to solar generation, enabling the college to turn this variable intermittent asset, being the solar, into a flexible, optimized resource when adding storage. This storage addition, as discussed, leads to a greater return on the solar project and lowers overall energy costs by charging off of the PV and shifting to battery power later in the day when utility prices spike and when the PV output would otherwise be declining. In this sense, the storage future-proofs the solar project from changing rates going forward and also participates in grid services such as demand response, which supports a more reliable electric supply for surrounding communities as well. And just one quick slide here on the STEM customer landscape. We work with a variety of Fortune 500 as well, and commercial customers throughout nearly every industry. We work with a host of top-tier partners and solar partners as well to collaborate on our solar plus storage projects and regional EPCs. So finally, to wrap up, we know that in today's complex energy matrix involving quite a few different business problems, there really is no one-size-fits-all solution to what's going on today. But at STEM, we're confident that our energy storage solution can help address many of these challenges that we've discussed. Storage is one of the most innovative ways to help reduce operating expenses, operate more flexibly, and improve resilience. These have long been a part of STEM's core value proposition and have helped our customers realize their financial, operational, and sustainability goals. So again, thank you all for joining us today. Really hope I have the opportunity to work with many of you on the webinar going forward. And now I'll turn it over to my colleague, Dana Christensen, who will talk more about how, on the technical side, the STEM solution works and how our artificial intelligence platform called Athena continuously adapts so our customers always maximize the benefits from energy storage.
Okay, thanks, Deandra. Let me take over with my screen. Okay, can you see it?
Yes, we can see it.
Awesome. Yeah, so as Deandra mentioned, I'm going to spend a little time today digging deeper into STEM's Athena software platform and how it can help customers adapt to changing conditions. So the way that we see STEM's role for our customers and ultimately in the energy industry is to optimize the performance of energy storage as well as other flexible energy assets. Storage really has the unique ability to act as both a source of energy load and generation. And so we see it as the natural control point for adaptive infrastructure. But however, as Deandra mentioned, we know that storage is not the only technology that our customer needs, and our controls integrate and co-optimize with other technologies such as solar, backup power, EV charging, and fuel cells, to name a few. Our controls will pivot around storage with these other elements, but use storage as the key element to balancing energy supply and demand in a way that ultimately maximizes revenues and cuts operating costs with respect to utility bills for our customers. So this is just a quick view into how our system works. We take in terabytes of data, terabytes of new data each day, and use that to inform our machine learning processes, or Athena, in order to forecast electricity supply and demand. And we do this at both a site level as well as a larger aggregate level in order to predict things such as coincident peaks that you might be exposed to. We then use those forecasts to run site-specific optimizations. And in fact, we run over 1 million optimizations per hour. So it's really a lot of learning for our AI. These optimizations are run against a configurable and dynamic model of the cost of electricity, which is based on each site's unique utility tariff. Based on that tariff, Athena determines the most economic times to charge and discharge the battery, and then sends that schedule down to our edge controller, down to the storage system itself, which is reacting in real time to real-time conditions. So our software and services are specific to each customer site. We're really customizing it, our solution, to maximize revenues at each site. Another thing to note is that our controls are hardware agnostic, we like to say. We work with top tier battery vendors in order to make sure that the hardware on site is also top quality, and we can achieve high performance with our software controls. Ultimately, our customers see results. As Deandra said, STEM has been around for a bit over a decade, and in that time, we've really hardened our product significantly into a proven technology. In 2019, we exceeded customer savings guarantees by 48%. And over time, our consistent performance has allowed us to secure over $650 million in project finance. And we also, in 2019, had a significant uptick in performance, as reflected by a 15% increase in year-over-year savings for our customers. So how do we get there? I'll give a little bit more color into our performance by looking at one of our customer sites. So as you, I'm sure, are well aware of, variations in utility load are obviously a driving factor for your utility bill. So this graph shows one of STEM's customer sites when it first joined our network. You can see the building load in green, the solar production down in yellow at the bottom, and then those tiny little bits of orange are Athena reacting and trying to chop off the load to get some peak reduction. There's really not too much activity going on, and therefore we aren't really saving that much for our customer during these first few weeks that they're on site. But this is the same customer site a few months later, and here you can see a lot more activity in orange of the battery. Athena at this point has learned and been able to adapt to the site's load profile and behavior and in order to be able to drive more savings for this customer. One thing I'll note as well is that this learning isn't just right at the beginning when we're onboarding a customer. but is happening constantly in real time. So when your site load changes in scale or shape, for example, as a result of COVID impacts, Athena reacts to this and adapts to continuously provide savings. So another big source of volatility, and Deandra was kind of touching on this, but is really your energy tariff. We see a lot of change in energy rates themselves, as well as the structure of energy tariffs. So you're probably very familiar with a simple time of use tariff, where you have different costs for both energy and demand at different times of the day, as shown by these two graphs. STEM is really experienced with operating these types of tariffs. And like Deandra talked about, we've also adapted to a lot of changes in these tariffs. When the highest cost peak time in California moved from early afternoon to early evening in 2018, Athena adapted and we were able to shift when we were discharging the battery in order to react to those change in time of use periods. Seamlessly reacting to these types of changes is really difficult for customers that don't have an energy storage system, and leaves them at risk of higher utility bills, really without any control. So Athena really provides a great solution in order to be able to give you back control and reduce your exposure to those types of changes. And we see other policy and rate changes in the works that will continue to add complexity to customer tariffs as our grid modernizes. One example of such complexity is what we refer to as event-driven tariffs. We see a lot of utilities putting customers on these types of tariffs by default. So customers on these tariffs, how it works is you get lower energy rates throughout the year, but in exchange, the utility will call specific events that have much higher costs during that time. So energy storage is really a great solution for this type of tariff. Athena will forecast that these events are coming and will reserve capacity as needed in order to maximize returns for that event. And then you can save money throughout the rest of the year on lower tariffs, but also save money during these high cost event windows because Athena is dispatching the storage. A final example of a complex tariff that STEM has experience operating is a type of tariff where customers are exposed either indirectly or directly to wholesale market prices. We see this with the VEDR tariff in New York, for example, the RTP tariff in California, or other customers who are just in deregulated markets and have a supply contract that expose them to energy prices that clear in the wholesale markets. The impact of this tariff is that there is more market exposure, of course, but then you have the ability to buy energy at perhaps lower real-time rates than you would be able to on a standard tariff. At STEM, for customers on these types of tariffs, we bring in this real-time or day-ahead energy price data into our system and build it into our optimization. That way we can effectively use the batteries to capture the arbitrage opportunity to buy low, sell high with that energy and ultimately increase returns. Now, these tariffs are all complex, but STEM's experience includes guidance for project modeling, tariff selection, and we help you design your project really in order to maximize customer savings for the whole duration of the project. We also work to continuously identify new opportunities for revenue generation, and Athena will continuously adapt to those new value streams that we add in, or any policy or utility changes with respect to tariff price or structure. So another topic that many of you, I'm sure, are probably curious about is just a bit more how our storage solution pairs with solar. Athena really works to optimize the flexible energy asset utilization, looking at both the solar and the storage with respect to how it can change the shape of the site load to maximize savings. Using local weather data and a physics-based proprietary algorithm, STEM forecasts the solar production for each site, and then that's pulled into the hourly optimization runs that I described earlier. When paired with solar, Athena manages the demand charges and leverages arbitrage value in the time of use tariffs. So as a result, we see that the storage reduces shoulder peaks, firms the solar, and shifts solar production to on-peak times. Many solar tariffs also include a net metering or a NEM export component, in which case Athena evolves around maximizing that net metering value by increasing export during the most valuable hours. On the flip side, some utilities prohibit any export of solar at all. This happens a lot in Hawaii with the HECO utility, for example. And then in that case, Athena solar self-consumption will enable increased solar sizing while also adhering to any interconnection rules. Additionally, our platform ensures that other constraints are adhered to in order to earn additional revenues. We help our solar plus storage customers realize the full value of the federal incentive tax credit and also earn regional incentive values such as Massachusetts SMART or California SCHIP, for example. And again, all of these constraints and tariff considerations are pulled into that optimization equation, which is run hourly and allow our customers to really enhance the value of their solar with storage. So I want to give you a quick view of the day-to-day story of what it's like to be a customer at STEM. We not only provide expertise and services to reduce operating costs, but we also want to provide our customers with the tools to really take back control of your utility bill operating expenses. So this is our user interface, which we call PowerScope. And I've added it really just to go over that at STEM, we want to be a partner to our customers, and we really care about maximizing performance at each customer site. So with this platform, we work with you to provide analytics and insights, and you can see there are some dashboards and reporting capabilities that help you analyze your site load, find any patterns with your site load, and also give you a view to manage the performance of your system. PowerScope is available to all of our customers, and we've heard that it really enables them with a granular view to understand their energy usage and costs. So to wrap this all up, this is all complicated, but STEM has the expertise to help customers reduce their operating costs, and experience really matters. Like Deandra said, we're operating at over 1,000 sites, and those sites span over 80 unique utility tariffs. So whatever tariff that your site might be on, we've probably seen it before. Our sites spread across 9 states, including New York and Massachusetts in the Northeast. And we also are in Canada and Japan. We not only provide revenues through utility bill optimization, but also through grid response programs. So really taking advantage of any value that could be added to the stack to provide revenues to our customers. And through all of these complex methods and experience, Athena really is a proven technology, and we have helped many customers achieve sustainability goals while reducing utility costs and minimizing their operating expenses. So with that, thank you, and I will pass this back to Steve.
Thank you, Dana and Deandra. Well done. Really appreciate that. I'm going to take one more shot at sharing my screen. Bear with me. Let me know if you can see it.
Yeah, we can see it now.
Okay, great.
Good morning, everybody, and thanks so much for joining our webinar. My name is Brian Kane, and I'm the Director of Enterprise Systems Engineering here at Bloom Energy. Joining me today are my wife, Sylvia, and my two children, Anya and Max, who graciously agreed to help me create this presentation for all of you. Where you find me standing is on the beautiful campus of Connecticut College. Behind me, in addition to my children, are 1.2 megawatts of Bloom Energy fuel cell energy servers, in addition to some electrical gear and appropriate communication systems to provide 24/7 by 365 clean power generation, delivering operational savings to Connecticut College. I'd like to take a moment to walk you through a single energy server. So immediately to Anya's left and coming back towards us are 5 power modules. Inside that power module is the core technology of the fuel cell manufactured by Bloom Energy. It is a solid oxide technology that electrochemically converts natural gas into DC electricity at an efficiency well above 50%. It is the most electrically efficient power generator ever invented at this scale. Anya is adjacent to one of those power modules, which is nameplated at 50 kilowatts. In the case of this system, you add up the power modules to get the nameplate of the energy server. This particular energy server could be nameplated at 200 kilowatts or 250 kilowatts. And the power modules are, in fact, populated such that we deliver predictable total output along with redundancy to ensure predictable performance of the system. Now, as Anya and Max take a step back, they are now standing next to the Bloom Energy illuminated logo. That is the inverter cabinet. Each Bloom Energy inverter comes out of the factory with a UL 1741 label. This is very important because it means that the system is already approved to electrically connect to all utilities in the markets in which Bloom operates. Generally speaking, all utilities recognize the UL 1741 certification as an acceptable certification to interact with their grids safely. Now, as they've taken the next step back, they're now standing next to the entrance of the system where the fuel is delivered to the fuel cell via a fuel processing module. Each energy server is identical, but for the number of power modules we connect behind the inverters. There could be as few as 4 power modules or as many as 7 power modules to create a 150 kilowatt to 300 kilowatt power solution, delivering predictable electricity. Now, let's take our attention to Max's right. Immediately before the video camera is the extension of the natural gas pipeline, which feeds this system underground. As I walked you through the energy server, the modules are connected with factory-provided cabling and pipes to distribute gas and electricity to and from the system before it is aggregated at the 480 volt level in the inverter. Where Max and Anya are standing, to Maximilian's right, is a 480 volt switchgear cabinet that aggregates the 5 energy servers on site into a common 480 volt DC bus and then connects to the green transformer, which transforms it to 13 kV here at the Conn College campus, distributing power directly to all of the consumption on campus. All of the components that you see here are provided, specified, and designed by Bloom Energy, although the transformers and switchgear equipment are off-the-shelf specified items that we procure from appropriate manufacturers throughout the United States. Now, I'm going to take a bit of a moment to walk you through the bigger picture design of the site. The energy servers are meant to be modular and redundant and to integrate with each other and with the site in the least impactful way possible. To my right, I walked you through one of the energy servers, but there are in fact 4 energy servers on the right and 1 energy server on the far left. As I walk along the energy server, if we could see through the steel overlays in the bottom of the systems, you would see the piping and the cabling that I described. As I noted, it's manufactured by Bloom Energy, everything above the concrete pad. It's delivered to the site, and then it's connected in a matter of minutes, I should say hours, to the inverter and the fuel processing module. Inside this power module, you will find, if we were to open the door, a fully integrated skid that includes the fuel cell technology and all of the relevant fans and monitoring devices to operate the fuel cell. When it is time to replace that fuel cell, there's 5 connections that are disconnected. The old fuel cell is removed and the new fuel cell is installed. This will occur for each power module roughly every 5 years. And it will always be performed by a Bloom Energy certified field service technician. So as I noted before, there's piping and cables provided by Bloom Energy to be integrated and placed on top of the concrete pad and connected to the inverter and the fuel processing module. As I walk further along, we are now walking along the next energy server, and as you can note, it is identical to the last, but oriented differently. As part of an optimization for cost and predictability, we have created these interconnected modules so that we can place them strategically on the campus wherever power may be required so that it is least impactful visually, while also maximizing cost performance by limiting electrical and gas runs wherever possible. Another thing I'd like to highlight is, in fact, this energy server and that energy server are 2 distinct systems that are back-to-back. This system is a standalone system that is configured in a different way to minimize its footprint of length and maximize and increase its width slightly to best fit the footprint. We have delivered nearly 400 megawatts of these systems in the United States and tens of megawatts of raw. We're delivering operational savings to universities in California, here in Connecticut, and other school systems throughout the Northeast. In addition to that, our clients consist of all types of industries that require clean, reliable, cost-predictive technology. One last note that I'd like to make is that the system, as it is a power generator and producing and delivering that power via inverters, can also be integrated with additional equipment manufactured by Bloom Energy to provide microgrid power. In the case of Connecticut College, they decided to focus exclusively on operational savings, but many of our clients are also leveraging our technology to integrate into an overarching reliability and microgrid strategy that incorporates our systems as the foundation of their business resiliency plan to ensure operation regardless of whether or not the grid is available to support them. So with that, I'm going to hand it back to the live presentation and we'll spend a few minutes on Q&A. I'd like to thank my family for their help in supporting this presentation, and I look forward to speaking to all of you in a moment.
Thank you very much, Brian Kane, and thanks everybody for your patience with the technical challenges there. As you could see, Brian was standing there with his family in the rain, and I don't think he'd ever forgive me if I wasn't able to play that. So thank you to Brian Kane and for a great video and for his family as supporting actors. So at this point, we are going to shift to the Q&A portion. We have about 20 minutes left, 19 minutes left. We'll get to as many as we can. But I've consolidated these questions and I'm going to direct them to the appropriate individuals. So the first question that came in is for, let's start with Mike, and then when Mike concludes, Deandra and this is very pertinent considering the unforeseen massive capital investment required by all schools to prepare to receive students in the next 6 to 7 weeks. But can you review and the procurement options for a Bloom fuel cell? Spend a little bit of time on that.
Yeah, thank you, Steve. So there's more or less two ways to go about procuring a Bloom project. The first one is the traditional way. You can buy it outright and cut us a check. Candidly, that transaction represents somewhere between 5 and 10% of our business now. What's far more popular is our power purchase agreement offerings that I alluded to during the presentation. In that type of scenario, there is no upfront capital expense at all by the customer. Bloom Energy installs the project completely from permitting, engineering design, construction, commissioning, to operating and maintaining the project for the full life of the project. And the customer does not spend anything until we've been generating electricity for 30 days. And then they'll get a bill from us, similar to the way they currently get a bill from the utility. And that represents the vast majority of our projects today, and also represents the vast majority of the projects we do in the higher ed space.
Mm-hmm. Great, thank you, Mike. Deandra, could you touch on this as well for a STEM solution?
Sure.
Thank
Thanks, Steve. And similar to as Mike laid out, at STEM, we have a few flexible financing options for our customers, one being the capital purchase for the system, all cash up front. Another being a power purchase agreement, should the storage and solar be procured together. So that would represent a more traditional solar type power purchase agreement if the configuration includes both technologies. And then third, we have what we call an energy services agreement. So a bit different from a PPA in that the customer pays STEM a fixed flat monthly fee over the duration of the contract. And so that represents the third option that is quite common as well, particularly if the customer is just looking to buy energy storage and there isn't solar involved or isn't another technology involved. So those are the main three that we transact.
Great, thank you, Deandra. Actually, the next question can also be directed to both of you, but Deandra, if you don't mind, if you could go first. Are there certain parts of the country that work better than others as far as the impact on economics and maximizing Opex savings?
Sure. And as I mentioned initially, currently STEM's install base is pretty heavily concentrated in California and in the Northeast of the US. I would say right now, in terms of STEM's current market transacting geographies, some of those Northeast states, particularly Massachusetts and New York, are really leading the charge with the rather sophisticated multiple utility programs in place to incentivize energy storage. I would say, if anything, they're quite a lot more progressive than California. Massachusetts, for example, our energy storage customers are juggling, if you will, 3 or 4 or 5 different value streams that are simultaneously deriving value for the customer. Part of that is from the more basic utility bill optimization and solar charging. Part of that is from National Grid and Eversource programs to incentivize that balance of solar plus storage, as I mentioned. So to answer your question, Steve, still I would say the Northeast of the US, with Massachusetts and New York being the top 2 in that region, and then California as well.
Okay, great. Mike, can you touch on this as well for a Bloom solution?
Yeah, with respect to saving money against your electricity bill, obviously it works best where the electric rates are highest. What we see from our customers is that's typically in California and in the Northeast. That said, we do have customers that will use us in lieu of legacy critical infrastructure and credit Bloom with helping avoid those upfront capital expenses. When you're in that type of situation, from what we've seen from our customers, we've actually done projects in places like Utah and North Carolina where power prices can range from 4 to 8 cents. So when you're looking at Bloom to, in addition to reducing energy costs, also reducing costs of legacy critical infrastructure, it can kind of work anywhere. But to reiterate, if you're strictly looking for OpEx reduction against your energy bill, California and the Northeast is where you want to focus.
Okay, great. That makes sense. Mike, I've got another one for you. You referenced the power purchase agreement. Can you talk a little bit about what's involved in servicing the fuel cell? And then are there any hidden or additional costs or anything like that?
You broke up there for a minute. I'm sorry. Can you repeat the question?
That's okay. Yeah, so you referenced the power purchase agreement as a procurement option. Can you talk about what's involved in service? Are there any additional costs associated if a customer were to move forward with a PPA?
Yeah, so there are no additional costs or surprises with respect to the PPA program. All of the service and maintenance associated with the system is included. From a service perspective, the only moving parts in the entire system are the blowers that we use to take in the ambient air. So there's really very little to do. We'll replace air filters on a quarterly basis. If you've ever replaced the air filter in a furnace, you're probably qualified to do it on a Bloom Energy server. We also have some desulfurization canisters where we take out the sulfur that the gas company injects into the natural gas flow to give it a scent. Our electrochemical reaction has no use for that. So those will be replaced every 6 to 12 months and sent to an EPA-rated facility for refurbishment and recycling. Mm-hmm. And as part of our power purchase agreement offering, you also get certain levels of performance guarantees. And as we start to approach those levels, we actually come out and replace the fuel cell tiles themselves. So those are the 3 major maintenance items that you can expect to see over the course of a Bloom project. All of those are included as part of the PPA program.
Great. Oh, that's great. Thank you, Mike. Deandra, I have a question for you about, both you and Dana touched on the impact of energy storage, both with solar and without, but can you talk about the economics? Do you need solar for the numbers really to work out as far as cutting OpEx?
Sure. Yeah, and solar has certainly been a big driver in STEM's past couple years of system configurations and interest. I think customer-wide, we're seeing an increased appetite for putting the solar and storage together, whereas maybe 4 or 5 years ago, our customers were really just buying storage on its own. Today, we still sell and design and install quite a few projects that are still storage on its own. We call them storage only. And so solar is not needed at all for the economics to make sense. And if anything, I think we're seeing in more and more utilities, I know I've mentioned Massachusetts a lot, but there are new program regulations for some utility programs such as MA Smart, where if a site is installing a PV array that is greater than 500 kilowatts, there must be a co-located energy storage system on site as well. So in that sense, we're seeing storage being more of a requirement for solar moving forward, but we have no requirement, so to speak, to install storage with solar to have the economics make sense. We still are able to generate substantial value for our customers just with a storage system alone.
Okay, that's a good answer. Thank you, Deandra. Another question, Deandra, I'm going to pose to you is, let's say there is a Bloom fuel cell installed, providing baseload power, cheaper, cleaner, more reliable power. How would a STEM solution add value if there's already an existing solution like?
Yeah, no, that's a great question, and obviously quite a relevant question for today's presentation. I think at STEM, and I would let Bloom address this as well, but at STEM, we like to think of batteries and fuel cells as complementary technologies, not competing technologies in any sense. We have a number of customer sites at STEM that have both batteries and fuel cells operating. the fuel cell, like you said, Steve, provides always on power. So that is a consistent level of output. The battery, on the other hand, charges and discharges to most effectively, sort of flatten the customer curve, if you will, and reduce those peaks that still exist after the fuel cell is installed and operational. I guess the edge case that I would give is if a customer's load, pre-fuel cell or pre-battery is perfectly flat. If we're looking at a data center, there is no need for a battery there. That's one case where a fuel cell can completely replace the load that would otherwise be procured from the utility. But if we're looking at any sort of higher education institution, a manufacturing site, an office building, really the majority of facilities that we look at, there is that variability, that load fluctuation that still represents substantial opportunity for a battery to come in and charge and discharge to really attack that remaining load that still exists after the fuel cell.
Okay, great. No, that's a good answer. That's pretty clear. We have one more question, and Mike, I'm going to pose this to you. There is an incentive that you referenced in your slide deck, LREC, Low Emission Renewable Energy Credit in Connecticut. We have some folks from Connecticut on the call. Could you talk a little bit about the impact that could have, and also the urgency, considering how many years are left in that program?
Yeah, thanks, Steve. So the Connecticut LREC incentive program, at least in my personal opinion, it is the best incentive program for fuel cells in the country. For those of you who aren't familiar, you basically get a 15-year contract from the electric utility to buy LRECs, low emissions renewable energy credits, that are generated by the fuel cells at a fixed price for the 15-year term. The way this works is you basically put in a bid on a dollars per megawatt hour basis. A lot of the bids that we typically see get awarded are in the $30 to $40 range, meaning you can get a 3 to 4 cent per kilowatt hour rebate from the electric utility locked in for 15 years. And in addition to that, you get a bunch of favorable net metering rules as well. There is a sense of urgency around the program this year. Next year is the last year of the program. Bloom has done over 50 projects in the state of Connecticut leveraging this program. We anticipate next year's program to be extremely competitive since it's the last year. So we're strongly advising customers that are in a position to move on a project this year to participate this year, since we anticipate bid prices being lower in 2021, given how competitive the solicitation will be in the last year of the program. All of that said, you don't have a lot of time to act at this point. The bids are due on July 13th. So if you are looking to move and take advantage of this program, you need to act quickly. You may have to put in some extra cycles over the holiday weekend here, but I can tell you it looks like it's going to be worth it. What we're hearing anecdotally from some other manufacturers is they aren't having the same level as participation as usual, given the pandemic. And that may lead to higher bid prices getting awarded. So it is a unique opportunity this year, given the pandemic, given next year's the last year of the program, to go ahead and participate and get maybe a higher bid than usual awarded.
That's great. Thank you, Mike. I appreciate that. So that is, and thank you, Mike and Deandra, for letting me pepper you with questions. That was our last question. So in closing, I really want to thank our speakers, Mike Mushaty from Bloom Energy and Deandra, Aversa, and Dana Christensen from STEM. We really are so pleased with the participation of two industry leaders that have so much experience with helping their customers cut OpEx, and really appreciate their time invested in this event. I also want to say a big thank you to all of the attendees for joining, but especially our higher education attendees for taking the time out of a very hectic schedule and preparing to receive students in 6 to 7, 8 weeks. As I said, we will be sending a follow-up email to all attendees with all questions and answers, but please follow up with Bill or me with any additional questions, or if something you heard today resonated and is something you want to dig into with a little bit more depth. To all of the attendees, we hope you and your family stay healthy and safe. And to the attendees that join from colleges and universities, we wish you the best of luck with your preparation for the fall semester and success in receiving students. This concludes Patriot Emerging Technologies webinar on lowering OpEx in higher education. Have a great rest of your week.